Solving general chemistry problems, thermodynamics. Without using enthalpy of formation data, estimate the standard enthalpy change for the following reaction. Using formation data, we can obtain very precise results for any reaction, providing the formation data has been measured and is available. In the absence of the data, for any reaction participant, average bond energies have been developed to provide a means of estimating the reaction enthalpy. In this case, we find an estimate of minus 113 kilojoules per mole. Here's another example. Now the stoichiometry has to be considered as with formation data. In this case, the estimate is minus 744 kilojoules per mole. So what are these bond energies and how can we use them? Let's start by thinking atomically about how a chemical reaction occurs. A chemical bond forms between two atoms only when they bump into each other. Atoms are always bumping into each other in the walls of their containers. Most collisions are unsuccessful in forming bonds and the atoms just bounce off. However, occasionally the orientation is just right and a bond begins to form as they collide. But if they are to stay together, they must shed some of their energy so that they do not bounce off. Through another collision with other atoms or molecules or walls, some of their kinetic energy is lost and they are now bound and begin to vibrate against each other. Ongoing energy loss allows the new bond to settle into its lowest energy state, and a new molecule has been born. If a chemical reaction is to occur, then some bonds in a reactant molecule must be broken before new ones can form. In this case, energy must be added to the motion of the atoms so that they can have enough kinetic energy to fly apart. Energy must always be removed from a molecule when a bond forms. Energy must always be injected into a molecule for a bond to break. This energy transfer can arise by collisions with walls and other molecules, by the emission or absorption of light energy, or by the flow of energy into or from other vibrations and rotations of the same molecule. Without stipulating how the energy arrives in the bond, a property known as the bond dissociation energy quantifies how much energy has to go into a particular bond to break it. This is directly related to the potential energy between the two atoms forming the bond. All bonds of different types have different strengths. Breaking the HH bond in the H2 gas phase molecule requires 435.93 kilojoules per mole. Breaking the Cl-Cl bond in the Cl2 gas phase molecule requires 242.58 kilojoules per mole. Breaking the oxygen-oxygen double bond in the O2 gas phase molecule requires 498.34 kilojoules per mole. Problems start to arise, however, when we look at the same bond in different molecular environments. The simplest would be the two OH bonds in water. It takes 498.7 kilojoules per mole of energy to break the first OH bond. The remaining OH bond, however, breaks with only 428.0 kilojoules per mole. You can perhaps appreciate that the electrons rearrange themselves differently once the first H atom is removed, and this leads to a different bond strength. The bond energy is different, but not tremendously so. When the bond dissociation energy of the same type of bond is measured in different molecular environments, one can find an average of all of them and produce what is called an average bond energy. If we look at all these CH bonds, and many more, the CH bond energy on average is about 414 kilojoules per mole. A table of average bond energies can now be used to estimate enthalpies of reaction in a similar manner when we used standard enthalpies of formation. Now, one caveat to mention, you will notice that different tables have different values. It happens since different workers may use different bonds to determine the averages. This kind of data is inherently uncertain, but it does have its usefulness. So how can we use this information? We use formation data by imagining the alternative reaction path of unforming the reactants into the elements in their standard states and then forming the products from those elements. With bond energy data, we imagine dissociating the reactants into the gas phase atoms and then assembling the products from those atoms. But there's one big warning at this point. Bond energy data can only be used for substances in the gas phase. They cannot be used if a substance is in a condensed phase, liquid or solid. This limits the applicability of this data. all reactants and products must be in their gas phase in order to use bond energies. Formation data, by contrast, includes the phase and has data for substances in all of their phases. This is an important restriction to remember when using bond energies. All is not lost, however. You can include additional steps using phase transition enthalpies, vaporization, fusion, etc., to get things into and out of the gas phase so that bond energies can be used. But that phase transition data must be available. So look at this problem. Estimate the enthalpy of reaction for the following. Ethane reacts with chlorine gas to form chloroethane and hydrochloric acid. We use bond energies by adding in the energy it would take to break all of the bonds in the reactants, and then we subtract out the energy that would have to be removed to form all of the bonds in the products. It is essential that we know the molecular structure of each species because we must be able to identify all of the bonds that are present in both reactants and products. This is the data we will need to use. Identify all of the bonds in the reactant molecules. You have to know what ethane is like structurally. There's one carbon-carbon bond, 6 carbon-hydrogen bonds, and then there's one chlorine-chlorine bond. Don't forget to break all of the bonds on the reactant side. To break all of those bonds, we would have to inject 347 plus 6 times 414 plus 243 equals 3,074 kilojoules per mole. And on the product side, we have one carbon-carbon bond, 5 carbon-hydrogen bonds, 1 carbon-chlorine bond, and 1 hydrogen-chlorine bond. To form then, we'd have to remove 347 plus 5 times 414 plus 339 plus 431 equals 3187 kilojoules per mole. Hence, our estimate of the overall reaction enthalpy is 3,074 minus 3187 equal to minus 113 kilojoules per mole. If we were to have used formation data, we would have found the answer to be minus 144.6 kilojoules per mole. The numbers are by no means the same, but they are in the same ballpark. They both confirm it is an exothermic reaction with an exothermicity exceeding 100 kilojoules per mole. In some situations, the kind of estimation given when using bond energy data is still useful, especially if some of the substances involved do not have formation data available. There are several differences that highlight the advantages and weaknesses associated with the two approaches. Accuracy. Bond energies are necessarily more uncertain than formation energies because they are averaged over many molecular environments. We use them to make estimates of reaction enthalpies. Formation data produces very accurate results, limited by the experiments measuring the tabulated data. Nevertheless, bond energies can tell us if the reaction is exothermic or endothermic. They can tell us if the reaction enthalpy will be large, medium, or small. It gives useful estimates in the absence of precise measurements, but we must always remember that they are more estimates than accurate calculations. Applicability. Bond energies can be used for all substances, while formation data must come from experimentally derived results. As long as the structure of the molecules are known, the enthalpy of a reaction can be estimated. With formation data, if one piece of data is missing, no calculation can be made. Algorithm. Formation data uses products minus reactants, while bond energies use reactants minus products. Formation data is based on making the substance, while bond energies are about breaking the substance apart, hence the different methods of applying the information. Phases. Formation data is recorded for substances in all phases separately. The enthalpy of formation of gaseous water is substantially different than for liquid water. Bond energies, however, can only be applied to gas phase processes. Any reaction participant is in a liquid or solid phase. Bond energies cannot be used. Atoms and elements. When using formation data, we imagine the reactants being unformed into the elements in their standard states. Bond energies, on the other hand, imagine gas phase molecules being dissociated into gas phase atoms. Elements, yes, but not in their standard states. No diatomic elements, no solids, nor liquids. Only the noble gases, which are very uncommon as reaction participants anyway, could show up as the same in both processes. Here's another example. The reaction between nitric oxide and hydrogen to form ammonia and water. Estimate its enthalpy of reaction. Here's the data that will be needed to solve this. A word of warning. You need to break all bonds in the reactants. That means you have to not only consider the molecular structure, but you must also take into account the stoichiometry of each species. This holds true for the products also. Here are the bond counts for both the reactants and the products, and a determination of the bond energies involved. The answer is reactants minus products, giving an estimation of the reaction enthalpy of minus 744 kilojoules per mole. If we were to use formation data, the result would have been minus 756.3 kilojoules per mole. Again, the value of bond energies arises when formation data is not available. Then a useful estimation can still be made.